All right. What's up, everybody? And welcome back to Structure Free Learning. So what we're going to do in this video is describe general curvilinear motion, and then we're going to describe position, velocity, acceleration in Cartesian coordinates. Let's start by considering a particle that's moving on a curved path. And it's going to look a little something like this. So here is my path in green. And it started somewhere over here and is moving along the path like this. I'll call that S. S will be the position along the path. My particle at one instant of time is right. And I can define its position from an origin. Yo, that's like 30 degrees. Not even planet. What? Yes. And this would be my position vector like this. At some later time, the particle moves over here. And here, its position vector is then described by, boom, r prime right here at some later time t. So my particle is here at time t, and it's moved to here at t prime. And, the vector, the increment of change, or that change in the vector, position vector r, would be just like this. This would be the position vector delta r right here. And that would be the change in my position, or the displacement of the particle from t to t prime. And the magnitude, or the change in position, this right here, this portion of the curve or the path would be delta s like this. And we can describe the instantaneous velocity as the limit as delta t goes to 0 of delta r delta t, which just tells me that the velocity vector, or the velocity, is dr dt. Boom. The one thing I would hope you get out of the video is that the velocity is always tangent to the path. Anytime that we have a particle that's moving on a path here, and if I have this little particle right there, boom, and there might be an origin over here, O, and the position vector would be defined from the origin to the particle at any instant, boom, like this. And the velocity vector, we know, will always be tangent to the path here, boom. And here, if this is my increasing position, this will be my velocity vector. Yes. All right. The speed of the particle is going to be defined as the magnitude of the velocity. And we'll typically denote that with just the v without the vector symbol above it. Or maybe you might be happier like this. And this would be v right here. And it would be equal to the change in the position dt right here. And change in the position of the path with respect to time t, ds dt here. And if I go back to this drawing right here, at one time, I'll have a velocity vector that's tangent to the path at t, right here. Boom, like this. And I'll call that v. At some other time, t prime, I'll have a velocity vector that looks like this, that's tangent to the path here, which I'll call v prime, like that. And if I took those two vectors off the board or off the paper, and I drew them with their tails touching, well, the change in velocity would just then be the vector between the two, in terms of vector addition. The change in velocity would be the change in this. And this vector right here would represent delta v. Boom, like this. And our acceleration, just like we did in 1D motion, our acceleration would be defined as the change in velocity with respect to time. And the acceleration, the instantaneous, would be limit as delta t goes to 0 of delta v over delta t, which would just be dv dt. And in terms of position, the acceleration vector would just be d2r dt squared like this. And so really all we have to note is that, hey, a lot of our 1D relationships hold, except now in curvilinear motion, because now we're moving on like 2 and 3 dimensions, we've got to use vector notation. So now that we've described curvilinear motion in general, that we know that there's a position vector, velocity vector, and acceleration vector, a lot of engineering dynamics, at least this first part of particle kinematics, is how do we describe position, velocity, and acceleration in various coordinate systems? And so the first way that we look at is in a Cartesian or XYZ coordinate system. Now, before I get going on this, I hope you'll take a minute to subscribe, like, and share, and continue supporting Structure Free. Also, I started an Instagram page or channel or Sight? I don't know. Who knows? But hey, I'll start posting like pictures from the mind of structure free. Yo, when we have a particle moving in a curved path, we have a position, a velocity, and acceleration. So we've got a particle that's moving on a curved path. In order for that particle to have a position, we have to have a reference. And so we'll choose this point as an origin or our reference. And the position vector would be defined from the origin to the particle. And then this particle will also have a velocity vector. And if it's increasing in position this way, I'll call this S, the direction of increasing path. You know, the velocity vector is going to be tangent to that path towards the direction of increasing position. So boom, here is my velocity vector. Let's say the acceleration vector is pointing this way, like this. Boom, like that. All right, so we have a position vector, a velocity vector, and an acceleration of this particle at this instant. And if we choose to use a coordinate system, like the Cartesian coordinate system, we might define an x, y, and z. Y is pointing up, x in the horizontal direction like this, and then z in this direction here. Out of the page, if you will. Boom. Here's my z component, like that, x, y, z. And because we're choosing a Cartesian coordinate system, well then now my position vector can be described in terms of like x, y, z coordinates. So it'd be like x I hat plus y j hat plus z k hat. It's x, y, and z positions. And all of these x, y's, and z's, these are time-dependent positions. They're functions of time. In order to find the velocity, I can use the definition of the velocity vector, which is dr dt, which would be the same as saying dx dt I hat plus dy dt j hat plus dz dt k hat, like this. Yes, and another way that we write this sometimes is through a dot notation, just a shorthand. It might be like x dot I hat plus y dot j hat plus z dot k hat, like this. Another way could be like v sub x I hat plus v sub y j hat plus v sub z k hat. These are all ways to actually represent my velocity vector here. But as you can see, all we're doing is taking a vector and breaking it up in its components according to the coordinate system that we choose. In the same way, we can do that with the acceleration vector, which would be the time derivative of the velocity or the second derivative of the position vector, all with respect to time. And again, this would just be all the representations that we can do, you know, just like we did with the velocity vector, we can do that with the acceleration vector. In terms of dot notation, it'd be x double dot for the second time derivative. Or we can write it in terms of ax, ay, and az. Yes, so just some basic definitions, you know, it's just a mathematical breakdown of our position, velocity, and acceleration relationships, right? And, you know, the power of this Cartesian coordinate system is that we're taking a 3D problem and breaking it up into 3 1D problems. And one dimension or one at a time is a lot easier than trying to figure out everything all at once. And the other thing that we're often going to be asked in our problems is to find like magnitudes. And so like the magnitude of position is the distance. This would be a distance. And, you know, to find that would just be the square root of some squares of the components, just like you did in calculus. This, and then for speed, the magnitude of the velocity is the speed, and you can just calculate that again by the square root of the sum squares. And very similarly, the magnitude of the acceleration by square root of some squares. All right, so that is curvilinear motion using rectangular components in a nutshell. Now, all you gotta do is apply it and do some problems. Check it out. Structure free.